Hey guys, when I last left you, we started our behavior system, and I told you that we'd be implementing FOV today. But since I got an amazing suggestion from MindPixel to create collision for our camera so that it wouldn't clip through the walls, I decided to make the FOV episode next time. I got to work implementing this system, and the end result is as shown on the screen. I'm sure this will help many of you in your own projects and games. This is a neat addition to the custom player controller we made last time. As you can tell, the camera collision is extremely efficient in detecting the best way to display the player in order for it to keep it in the view at all times. And if it does get too close to the player, the transparency of the player is modified to suit the situation. It can be used in any complex situation such as narrow gaps and hiding behind walls. As you can see, if you comment and suggest an idea, it will be taken seriously. So please, if you have any ideas, leave it down below in the comments. If you haven't already, subscribe to keep up with the original content, and let's get right into the tutorial. Alright guys, let's begin. So when we last left off, our camera controller was like this. We could move freely and perfectly, but if we went up against a wall, for example, and we rotated the camera, we can see that our player is nowhere to be seen. It is actually behind the wall, and this is a very important problem to tackle in third-person games, as it is very necessary to always have the player in the view at all times. So the way you would tackle the solution, let me just pause the game here in this current state and go to top view, and I'll give you a proper explanation of how a problem like this would be solved. Okay, so we have our camera over here and our player over here. So to detect if the camera cannot see the player, we don't need to do any fancy math or trigonometry like some other videos have used. All we have to do is a simple raycast from the player in the direction of the camera, and as soon as we do that, we can see that the ray actually hits the wall, and we get this point over here, and this is the point that we need to move our camera to in order for us to be able to see the player. And as you can see in the camera preview, if we move to that point, well, we can see the player. And obviously it does get a bit more complex than that, but that's the basics of how it works. So then some other features that we're going to add to that solution is that if the camera does get too close to the player around here, if it gets too close, then what we are going to do is we are going to reduce the transparency of the material or materials on this object to a lower percent, so that we can see through the player, so we know where the player is, and we also have awareness of the surrounding space around the player. Another problem we're going to be tackling in this episode is when we are backed up against a wall and our player camera when we're backed up against a wall and then we do a ray to the camera, as you can see, the camera will be right next to the player, and even if we have transparency, it won't look good. So if we're in a situation where the camera is backed up against a wall and so is the player, we will detect the situation and the camera will be lifted up and then rotated downwards, and then we will be able to see the player from this angle over here. Okay, so that's also a very nice feature that we have added, and let me explain to you how to set up this scene first. Just add this wall and get rid of all of your other elements, and this will be enough to test most of our features, including the slope. And then what you're going to do is you're going to click on this camera here, and then on the clipping planes, you're going to change the near. You're just going to type in 0, and it will change back to the lowest clipping plane it can allow. And basically what this will allow us to do is have it right up near the wall and make sure it still draws the wall. As you can see, if I increase this clipping plane, as you can see in my camera preview, it decreases the wall, and this won't look good. It will look like you're actually clipping through the wall, and we don't want that. So set it to the lowest amount you can, and you have to, and it'll always look like you're against the wall. Okay, and then we're gonna go to our camera controller that we have from last time, and I did change a few settings. So I changed the mouse sensitivity to 10.48 and the distance from target to 6.42. That is my personal preference. I like that, and it works quite well with collisions. So I like that, and I'm gonna keep it. And let's get right into the coding. Okay, let's open up the mono develop file and let's get right into it. So before we begin, I'm just gonna add some collision variables, and I'm just going to add all the variables like usual, and I'll explain what they do, and this is going to be fun. So let me write the first few variables. So I'm just going to call this transparency, and then I'm going to write public bool change transparency, and we're going to set this to true. So basically this will be a little check if the user actually does want to change their transparency as it gets close. And let me remove that extra bracket over there, and then let me make another public variable called public mesh renderer, and we're gonna get in the target renderer, and we're gonna pass in the player's mesh renderer into that so we can change the transparency of its materials easily. And then we're gonna add a header called speeds, and we're gonna add a float called move speed, and we're gonna set that to 5, and we're gonna add another float called return speed, and we're gonna set that to 9, and we're gonna add another variable called public float wall push, and we're gonna set that to 0.7. So basically, the move speed is when you're colliding against a wall, how fast you collide against a wall and slide against that wall. The return speed is when you're no longer detecting collisions, how fast you return to the original state of the camera. And the wall push is basically when our ray detects the wall, it will find the normal of the wall. So every normal of a face is detected like this. So the outward direction, the direction that the face is pointing in. And when we find a ray against a wall, it will push out in the normal distance by 0.7. So it's an extra prevention that we're not clipping into the walls. Okay, now that that's explained, let's go on to the next variables. And we're going to go add another header called distances. And we're going to add a float called closest distance to player, and we're going to set this to 2. So this is basically when our transparency starts to kick in. And then we're going to add another float called even closer distance to player, and we're going to set this to 1. So this will be basically when our distance stops working. So basically, if we are clipping against the ground and we are moving in the direction of the player as the collision would work, we don't want it to clip through the player. We want it to stop at a certain distance away from the player, and that's going to be our even closer to player. So once we reach this point, for example, it won't be able to move any closer to the player. So this makes sure we don't go into the player as such. But sometimes it goes into a forced situation where that has to happen, and that's why we rotate down and go above the player. Okay, let's add another quick variable, and we're going to call this public layer mask collision mask. This will make sure we are not colliding, the ray isn't colliding with the actual player. Okay, so let's add a private variable, and let's call this pitch lock. So basically, pitch lock is when we detect that we need to lift ourselves up and point ourselves downward, and when we're in that situation, it'll force a 90-degree pitch onto our pitch, but still allow for us to use the horizontal movement. Okay, so I'll explain how we're gonna implement pitch lock just now. So we're gonna say if we're not in pitch lock, we're going to do the original stuff, but we're going to drag this into here. And actually, no, scratch that. We're not going to be using vector3.smoothTheDamp anymore. We're going to be using vector3.lerp because that works way better with collisions and looks nicer. So let's do current rotation is equal to vector3.lerp, and current rotation, we're going to pass in a new vector3 of pitch and yaw, and we're going to pass in the rotation smooth time times time.delta time. And since we're multiplying by times.delta time, we're going to have to increase the rotation smooth velocity, and I'm going to set it at 8, as that worked well for me. Okay, and now we're going to do else. So if we are in pitch lock, then this is what we're going to do. We're going to copy the yaw and paste this in here because we will be able to move it across that axis still. But we're going to go pitch is equal to pitch min max, and we're going to go y. So basically what this is we set a maximum pitch. Where is it here? We set a maximum and minimum pitch, and basically we're going to clamp it to the maximum pitch as soon as pitch lock is on. So it won't be able to move away from that. We're going to copy current rotation and just paste it in there. Okay, now let's get into the actual coding. But before we do that, I'm just going to cut this, and we're going to put it at the top of this function because it works better at that position, and it's better if we update the position and then the rotation. Okay, now let's create our main method, private void collision check, and we're going to pass in a vector3 or red point, and that's going to be our return point. And what we're going to do is we're going to go here and remove transform the position equals, and we're going to go collision check, and I'm going to pass in this whole vector, and boom, we have a little function that handles our collision. Okay, now let's start the real implementation. We're going to go raycast hit, and we're going to store an empty variable there for our hit. We're going to go if physics.line cast, not raycast. We're going to do a line cast because we know the starting and end position. So we're going to go start from target.position and finish at ret point. So ret point is basically the predicted position, not the position that we are in, but the predicted position. That is extremely important because if we keep checking from our current position, we won't be able to move anywhere. And then we go out, hit, and then I'm going to pass in a collision mask, and then we're going to go down. Okay, and we're going to collect our normal data, and we're just going to call that norm, and we're going to create a new vector3, and hit.normal.x, hit.normal.y, and I don't know why I am doing that. I should just go hit.normal times wall push, and this will give us our normal data. And then we're going to go vector3p equals hit.point plus norm. So basically that's our whole function so far. What we can do right now is, if our camera is here, like I explained before, if our camera is over there, we line cast from here to here, it hits this point for example, and it pushes outward, and this would be our little point where our camera would be right now. So we have our basic collision right now, but we need to do some checks to make sure that we're actually in the right place and we're not going too far. Okay, but before that, I would like to add a little method called a transparency check, and the private void full transparency. Alright, so basically what we're going to do in transparency check is we're going to lerp down the transparency, but we'll do that after we check if our distance is too high or too low. So let's call transparency check here. When we go if vector3.distance vector3.lerp, and I'll explain what we're doing in just a second. Time to delta time, target position is lower than or equal closer. Okay, so this vector3.lerp is where we will move if we are not too close to the player. So let's copy this. And if we're not too close to the player, then we're going to set the transformed position to that value. So if you understand correctly, oh no, what am I doing? Sorry about that. So this is the vector3.lerp, and we're going to check the distance from the future predicted position to the target position. And if the future predicted position is lower than or even closer to distance variable, then we won't be able to do anything. If it's not, then we'll move the camera to that position. So we'll be moving it to the point at a speed of move speed times time to delta time. And we won't just pass in p here because that's inaccurate, because we're actually moving by a lerp, which is gradual over time. Okay, and what we're going to do is we're going to return here to make sure that the next statement won't be called if the previous statement was true. And we're going to pass in full transparency here. And we're going to go transform.position equals vector3.lerp, change transform.position, red point, and return speed times the time.delta time, and pitch lock is equal to false. So let me explain what's going on here. Okay, so if the line cast had returned nothing, okay, there is no wall, there is no problems, it just returns our original vector, which is what we were using in the previous camera controller anyway, and then that is just lerped from the current position to that point at a different speed, which is return speed, okay? And basically, if there is no wall, nothing, we can automatically set pitch lock to false. Okay, now let's work on the transparencies. Very easy, and let me just explain how this works. Well, let's just add our little if change transparency, because some people might not really want transparency. And let's go if vector3.distance between transform.position and target.position is lower than or equal to closest distance to player, else. Okay, so we can just write a little method for each instance. So if the current camera position is lower than the closest distance to player, then we'll render the transparency a bit lower. But before we do this, in order to make this work, let's just do a few things. First, let's go into our main camera and make sure the target renderer is attached, and then let's make sure all the other variables are satisfied. Collision mask is not, so let's click everything and deselect player like usual. Okay, so let's click on our little capsule here and let's go into materials, and I'm gonna create a new material called player material. And you gotta understand that fading only works when you click here, and on rendering mode you click fade, and you have to click that if you want to be able to change the opacity. But if this won't work for you, there are heaps of other methods to change the opacity. Just search it up online and you'll find heaps of hits. Okay, so I'm just going to change is when we bring down the A value, which is the alpha value, we bring that, as you can see, we start to fade out. The shadows do get the dots. That's because I'm on medium quality. What we have to do is increase the quality of the render and it will be normal. So as you can see, we can fade out and in as we go. Okay, so now we know how to do that. Let's get into changing it. So if the distance is low, we're going to create a new temporary variable to target render dot shed material dot color. As we can't change the alpha value directly from the material, we have to create a temporary variable and then change it from there and then change the full color. So we're going to say temp.a equals mathf.lerp. So basically it's like vector3.lerp, quaternion.lerp, but it's the base for all lerping functions. So we're going to go temp.a and we're going to change the opacity to 0.2f. I've seen this works well, but it's between 0.0 and 1 if you want to change the transparency higher or lower, and we're going to do times. So basically we're going to lerp the alpha value from the current to 0.2f by the move speed times time dot delta time. Easy stuff there. And then all we're going to do is we're going to get a target renderer dot shed material dot color is equal to temp. And let me explain. Most complicated players have more than one material on the same object. What we have to do to solve that issue is you would, instead of doing this just for the shed material, you would loop through. So as you can see, there's another variable here called shed materials, and you would loop through that every frame and see if that condition is met, and then you would create a temp for each variable inside that loop. But that's not really what I want to do because I also have to record, and I don't think it will be the best performance upgrade for me. Okay, now what we're gonna do is we're also here, we're gonna say if, no, we're not actually gonna do that. Yeah, let's just go here and say if target renderer dot shed material dot color dot a is lower than or equal to 0.99f, then we're going to update it to a higher value because we don't want it always updating for no reason. Okay, so we're going to do the same thing over here. We're just going to copy this whole thing and paste it here, and instead of 0.2f we're just going to change it to 1, and then we have a perfect little system here. Okay, alright, easy stuff. And all we're going to do now is we're going to copy this whole system and we're going to put it in here. We're going to get if change transparency, then we're going to call this. So basically when full transparency is called here, then it changes back to full transparency. Easy stuff. So we basically have a simple transparency plus collision system, but there's one other main thing that we have to add, and that's the pitch locking. So we're going to create another private void. Let me fold up all of these and create another private void, and let's call this wool check, and let's go up here and add wool check before we forget to add it and wonder why our function isn't working. Okay, let's add a ray and create a new ray, target dot position and negative target dot forward. Let me explain. Okay, so basically what's going to happen in order to check for walls and the situation that I described before, if we're right up against the wall, all we have to do is send a ray from here to the backwards direction, so back here, and once we detect a ray in like the range of 0.7, then we know we're backed up against the wall and the camera won't look good there, so then we'll automatically set pitch lock to true. Okay, and we're gonna go ray cast hit, and we might want to do a sphere cast, because if we're in a situation like this, we're still backed up against the wall, but our center isn't actually going to detect the wall, so we'll be clipping against this wall and the camera won't know. So that's not a very good situation to be in. So let's just go if physics.spherecast ray, and we're going to set the radius to 0.5, and then we're going to go out hit, and then the max distance we're going to set to 0.7. But if you need more distance on your walls and you see the walls aren't showing up properly, just increase that distance, and then you can go collision mask. Alright, and then all we're gonna do is pitch lock equals true if it detects a wall, and if you don't detect a wall, we'll go else, we'll go pitch lock is equal to false. So if it detects a wall, we're gonna pitch lock, and if it doesn't, we're gonna not pitch lock. Okay, and then we have our pitch locking function here, and everything should be working as we want it to. If we did everything okay, let's check it out. Oh, as you can see, our camera did clip onto the side. Oh, we're having some issues with movement. The rotation smooth time still stayed at 0.12. Sorry about that. We can't just change it in script since it's a public variable. Let's change that to 8. But as you can see, the camera was on the other side and now we're on this side. Okay, so let's see this. Let's see how much this works. And as you can see, that's perfect. We are backed up quite close to wall. So when we are about to clip, we change it into this place over here. Okay, let's check that one more time and boom. And since I am recording, you can see that I'm having some lag, but this won't happen in yours, of course. But if you feel like the movement is too, smooth or something, you can always change the variables. Everything is open. And then let's see if we actually collide against the wall. So let's move backwards. You can see that we're not moving even further away, and we are colliding against the wall. And what about transparency? There we go. We are changing transparency as well, and that's quite amazing. So if the player gets too close, we can change the transparency, just see through it. And remember, you have to change the materials to fade or transparent, and both is fine, both will work. As you can see, we're always changing based on the situation, and it's amazing. And you can see that it's detecting collision on slopes, and some of you might not want this, and all you have to do is change the radius to around 0.2, and if we play it now, we will be able to realize that it doesn't change on slopes, and we can get up close to it, and we can change all the distances to suit how we want. So if I change it even closer to distance player to 3, we can see that we can't get closer to the player no matter how much we try. Okay, so, and even if it gets close, we just get pushed up. Alright, and this will work in many complex situations. So let me just create a little demo corridor here.